The Pacific does not announce itself. It simply expands. Beyond the last trace of coastline, beyond shipping lanes and satellite towers, the horizon dissolves into a seamless ring of blue. Here, there are no landmarks, no reference points, only curvature, subtle, planetary, immense. The Pacific Ocean covers more than 1/3 of the Earth's surface. It holds over half of the planet's open water. Its average depth approaches 4,000 meters, and in its deepest trench, it descends nearly 11 kilometers into darkness. Every square kilometer absorbs solar radiation hour after hour, storing heat in quantities that dwarf the atmosphere above it. A vessel moves across this surface. From space, it would be invisible. From the deck, the ocean appears calm. Swells roll beneath the hull, spaced far apart, the kind generated by distant weather systems days ago. These waves are not wind-driven chop, they are traveling energy. Each swell represents momentum transferred from air to water somewhere far beyond the visible horizon. The Pacific is never still. It is always transmitting force. Sea surface temperatures here hover above 28 degrees Celsius. That number matters because 26.5 degrees Celsius is the threshold at which tropical cyclones can begin to organize. Warm water fuels evaporation. Evaporation feeds atmospheric instability. And instability, when conditions align, becomes rotation. But for now, the air is steady. The barometer shows no sudden drop. Clouds remain high and scattered. The illusion is perfect. Yet the Pacific is not a passive body of water. It is a thermal engine, vast, layered, and constantly exchanging energy with the atmosphere above it. Beneath the surface lies a warm upper layer, perhaps 50 to 100 meters thick. Below that, temperature declines sharply across a boundary known as the thermocline. This gradient stores potential energy, separating warm, buoyant water from the cold density below. If that boundary is disturbed, enormous heat can be released upward. The ship continues forward, unaware that thousands of kilometers away, a subtle imbalance has already begun. It starts with pressure, a difference so small it would go unnoticed without instruments. A drop of just a few millibars across hundreds of kilometers of atmosphere. Air always moves from high pressure to low pressure. When a region of lower pressure develops over warm water, surrounding air begins to flow inward. On a non-rotating planet, that air would travel in a straight line. But Earth rotates, and rotation bends motion. This deflection, known as the Coriolis effect, causes moving air in the northern hemisphere to curve to the right. Instead of rushing straight toward the low pressure center, wind begins to spiral around it. At first, the circulation is broad and disorganized. Clusters of thunderstorms flare and collapse. But the ocean below continues feeding moisture into the system. Warm surface water evaporates rapidly in tropical sunlight. When that vapor rises and cools, it condenses into cloud droplets, and in doing so, releases latent heat. That heat warms the surrounding air column, causing it to rise faster. Rising air reduces surface pressure even further. Lower pressure strengthens inflow. Stronger inflow increases evaporation. The feedback loop tightens. High above the forming system, thin cirrus clouds begin to spread outward, the first visible signal that a vertical engine is building below. These outflow bands vent excess air from the top of the storm, allowing pressure at the surface to continue falling. On deck, the change is subtle. The wind shifts direction slightly. Swells lose their uniform spacing. The air feels heavier. Humidity climbs. The barometer ticks downward, slowly but steadily. The Pacific does not erupt into violence without warning. It reorganizes. And reorganization is already underway. Within 24 hours, the structure becomes visible from orbit. A circular mass of deep convection consolidates around a tightening center. Bands of thunderstorms wrap inward in curved arms, marking the beginning of cyclonic symmetry. At this stage, the system is classified as a tropical depression. Sustained winds remain below 63 kilometers per hour, but pressure continues to fall. As long as sea surface temperatures remain high and vertical wind shear, the change in wind speed with altitude stays low, the storm can intensify. Wind shear is critical. Strong shear can tilt the developing vortex and disrupt its vertical alignment. But here, conditions are favorable. The atmosphere above is relatively stable. The heat below is abundant. The storm strengthens into a tropical storm. Winds exceed 63 kilometers per hour. A name is assigned. Rotation tightens. The central pressure drops below 990 millibars. Physics accelerates. The pressure gradient, the difference between the low pressure center and the surrounding atmosphere, determines wind speed. The steeper the gradient, the faster the air moves. And as air accelerates inward, conservation of angular momentum increases rotational velocity, much like a spinning skater pulling in their arms. Cloud towers rise 15 kilometers into the troposphere. Lightning flashes within the dense convective core. The ocean surface begins to respond visibly. wind stress transfers kinetic energy directly into the water. Waves grow taller and steeper. The distance over which wind blows uninterrupted, known as fetch, allows wave energy to build exponentially. Once sustained winds exceed 119 kilometers per hour, the system is classified as a typhoon in the Western Pacific. If winds surpass 240 kilometers per hour, it becomes a super typhoon. The Western Pacific produces more of these systems than any other ocean basin on Earth. The reason is simple. It contains the largest continuous reservoir of warm tropical water on the planet. The ship now feels the change. Wave intervals shorten. Spray lifts from the crests. The horizon tilts unpredictably. Rain begins, not as scattered showers, but as dense bands rotating inward. Visibility narrows. Sound changes. Wind no longer whistles, it roars. Above, the storm organizes into near symmetry. A dense central overcast hides what is forming at its core. An eye is beginning to take shape. And once the eye wall closes, the ocean will no longer resemble the one the vessel entered. The Pacific has converted heat into structure, structure into rotation, rotation into force. And this is only the beginning. typhoons arrive, the ocean no longer resembles a surface. It becomes terrain. Wind exceeding 120 kilometers per hour does not simply push water forward, it transfers momentum continuously into the sea. Through frictional drag, the atmosphere forces energy into the upper ocean layer, increasing both wave height and wave steepness. The longer the wind blows across open water, the greater the fetch, the more energy accumulates. Pacific, fetch can extend for thousands of kilometers. There are no coastlines to interrupt growth. Waves begin to interact. When two wave systems overlap, one generated locally by storm winds, another arriving as long-period swell from earlier phases of the system, they can combine through constructive interference. For brief moments, their amplitudes add together. This is how rogue waves form. Not myths, not anomalies, but mathematics in motion. Individual waves can rise to more than twice the significant wave height, meaning that in a sea averaging 12 meters, isolated peaks can exceed 20 meters. Walls of water rise without warning, shaped not like smooth hills, but jagged, wind-torn ridges. Spray shears from the crests and becomes airborne. Visibility drops below 100 meters. Rain bands rotate inward in diagonal sheets, each one carrying embedded microbursts, sudden downdrafts that slam into the surface and explode outward. pattern. Wave direction shifts unpredictably as wind vectors curve around the strengthening circulation. Instead of orderly sets, the vessel encounters cross seas, waves colliding from different angles, creating pyramidal peaks and troughs that open like moving canyons. Below the surface, turbulence deepens. Storm-driven mixing penetrates tens of meters downward, weakening the thermocline. Cold water begins to rise. Iron and nitrates trapped below are stirred upward, invisible now, but biologically transformative later. Above, however, biology is irrelevant. The ship climbs, pauses, then drops. Each descent carries acceleration forces capable of damaging structural integrity. When a hull falls into a trough and slams into the next rising wall, impact loads can exceed design tolerances. Steel bends, fastenings strain, equipment tears free. The Pacific is no longer vast and abstract. It is immediate and closing in. On satellite imagery, the eye wall appears as a perfect ring of convection, a circular barrier of the most intense winds and rainfall on Earth. But from sea level, it is not a ring. It is a moving mountain range of rotating violence. speeds now exceed 200 kilometers per hour. Central pressure has fallen below 930 millibars. That number matters more than the wind, because pressure difference is the true engine. Accelerates toward the center due to the pressure gradient force. The steeper the gradient, the faster the inflow. As that air spirals inward, conservation of angular momentum increases its rotational velocity, tightening the vortex further. The result is the eye wall, the zone where upward motion, condensation, and rotational speed all peak simultaneously. Here, wave formation reaches its extreme. Sustained wind stress over fully developed seas can generate significant wave heights exceeding 15 meters. In super typhoons, measured waves have surpassed 18 meters. Individual crests can rise even higher. But height alone is misleading. It is the steepness that destroys. Shorter wavelengths mean sharper angles. Instead of rising gradually, waves become near vertical faces. The vessel no longer rides the ocean. It is lifted almost upright, then released into free fall. For seconds at a time, gravity is the only force acting on it. Then, impact. The sound is not water, it is a detonation. Rainfall in the eye wall can exceed 100 millimeters per hour. Visibility collapses to near zero. The sky and ocean merge into a single gray void. There is no horizon, no up, no down, only rotation. The structural symmetry of the cyclone means the eye wall encircles the calm center completely. There is no safe gap. The ring must be crossed. Lightning flashes horizontally inside the dense convection. Electrical discharge triggered by intense vertical motion and ice particle collisions high within the cloud towers. gust carries kinetic energy equivalent to a moving wall. Each wave carries mass measured in thousands of tons. The Pacific is not angry. It is converting thermal imbalance into mechanical force with ruthless efficiency. And the vessel is inside the engine. Abruptly, it stops. The wind collapses, rain thins. The sky opens overhead into a circular window of pale light. This is the eye. At the center of the cyclone, air descends instead of rising. As it sinks, it warms and dries, suppressing cloud formation. The lowest atmospheric pressure exists here, sometimes below 900 millibars in the most intense super typhoons. Paradoxically, the calmest air surrounds the most violent system. The sea does not immediately settle. Swells continue rolling inward from all directions, remnants of the eye wall still rotating around the perimeter. But compared to what came before, the stillness feels unreal. This is the most dangerous illusion. Because the eye is not an ending, it is an intermission. Cyclones are symmetrical systems. The backside eye wall approaches with winds often equal and in some quadrants stronger than the front. In the northern hemisphere, the right front quadrant of a moving storm typically carries the highest wind speeds due to the addition of forward storm motion to rotational velocity. But as the vessel drifts through the center, orientation becomes uncertain. The barometer reads its lowest value. The crew may believe the worst is past. Above, The circular wall of cloud rotates silently around the clearing sky, a stadium of condensed energy waiting to collapse inward again. The physics has not changed. The heat source remains the same. The gradient still exists. And within minutes, wind will return from the opposite direction, reversing wave vectors, colliding with residual swell, creating a chaotic cross pattern even more unstable than before. The Pacific offers no recovery time, only the next phase. Returns without warning. Not gradually, not gently. It strikes from the opposite direction. The backside eye wall is often as violent as the first, and sometimes more chaotic. The ocean surface, already destabilized by hours of sustained wind stress, now receives force from a reversed vector. Residual swell from the forward quadrant collides with new wave growth generated by opposing winds. This is cross-sea amplification. Wave trains intersect at sharp angles, producing unstable pyramidal peaks. Instead of long ridges, the sea fractures into moving geometry. Crests rising in triangular forms, troughs opening abruptly beneath the hull. The vessel no longer climbs predictable slopes. It is struck laterally. Roll angles increase. Structural fatigue becomes measurable reality. Steel fatigues not from single impact, but from repetition. Each flexion introduces microfractures. Each slam transfers kinetic energy into frame joints, weld seams, anchor points. The human body experiences the same principle. Balance deteriorates, reaction time slows, muscles strain to compensate for constant instability. Wind speed remains above 180 kilometers per hour. But now, fatigue becomes a factor. Not just for the crew, for the storm itself. As the cyclone churns across the ocean, it extracts heat from the surface layer. Strong vertical mixing draws colder water upward. This process reduces sea surface temperature beneath the storm core, sometimes by several degrees Celsius. And a tropical cyclone depends entirely on warm water. In a sense, the storm begins to weaken the very fuel source that sustains it. Yet weakening does not mean gentle. Rainfall remains torrential. Gust fronts sweep outward in bursts exceeding sustained wind speeds. The vessel endures sustained acceleration, followed by abrupt deceleration as hull meets water mass measured in thousands of tons. Navigation systems flicker, satellite communication drops intermittently. The world narrows to steel, water, and force. The Pacific is no longer vast, it is immediate and mechanical, and it is testing limits. Later, the gradient begins to relax. The barometer rises slowly. Wind velocity drops below 150 kilometers per hour, then below 120. The symmetry of the cyclone deteriorates. The once defined eye wall fragments. Convection becomes asymmetric as dry air intrudes into the circulation. Without continuous latent heat release, the vertical engine weakens. Physics demands equilibrium. As the pressure difference decreases, so does wind acceleration. As surface waters cool, evaporation declines. Without upward heat flux, rising columns of air lose intensity. The storm does not die dramatically. It unravels. But the sea does not calm instantly. Energy already transferred into the water continues propagating outward as swell. Long-period waves generated at peak intensity radiate away from the storm center at speeds exceeding 50 kilometers per hour. These swells can cross entire ocean basins, reaching distant coastlines days later. What feels like an ending here may become hazardous surf thousands of kilometers away. surface, the ocean has changed. The upper mixed layer has deepened. Nutrients stirred upward will fuel plankton blooms in the coming days. Oxygen levels shift. Temperature gradients reorganize. A storm is not an isolated incident. It is a reconfiguration of the upper ocean. The vessel now rides lower waves, still powerful but organized again into discernible rhythm. The horizon reappears as a stable line. Rain thins to scattered showers. The roar fades into wind, then into movement, then into space. Morning light returns gradually. Cloud bands stretch thin across the sky, no longer spiraling but drifting. The Pacific appears wide again, calm enough to deceive, but the data tells another story. Satellite measurements will show a cooled sea surface footprint tracing the storm's path, a scar of reduced temperature several hundred kilometers wide. Wave buoys will record peak significant wave heights long after the eye wall has collapsed. Atmospheric models will log the minimum central pressure and the duration of maximum sustained winds. The storm becomes numbers. But for those who crossed it, it remains dimension. Scale is restored slowly. The vessel continues forward, not because it conquered the Pacific, but because it endured one cycle of its mechanics. The ocean has not changed its nature. It has simply redistributed energy as it has done for millions of years. The Western Pacific will generate another system. Warm water still stretches unbroken across thousands of kilometers. Solar radiation continues. Trade winds continue. Rotation continues. The conditions that created the storm still exist. That is the true scale of the Pacific. Not a single wave, not a single typhoon, but a planetary engine capable of reorganizing atmosphere and ocean with simple physical laws applied across enormous space. As the sea settles into long rolling swells once more, the illusion returns. Blue, open, endless. But now the vessel understands something it did not at departure. Calm is not safety. It is merely a temporary balance between forces too large to see all at once. The Pacific does not threaten, it operates, and survival within it is not about dominance, it is about respecting energy measured in heat, pressure, and motion unfolding across the largest body of water on Earth. The horizon remains distant, the engine of the ocean continues, and somewhere beyond sight, warm water is already rising into the sky again.